In the previous video, we concluded with Hans Bethe's calculation of the Lamb shift. It demonstrated that the vacuum fluctuations predicted by quantum field theory have an observable impact on hydrogen energy levels. A key step in the calculation is that Bethe applied mass renormalization to compensate for the infinite electromagnetic mass of a point electron. However, the infinity was not completely removed, because the simplified calculation assumed a non-relativistic approximation. The result served to make plausible that a fully relativistic theory would completely remove the infinities and accurately predict the Lamb shift. Robert Oppenheimer summarized the challenge of finding a satisfactory relativistic theory during the Solvay Conference of 1948. When we tried to remove an infinity by subtracting another infinity, the result is typically ambiguous, because infinity minus infinity can give any value, depending on how you take the limit. As problems become more complex, it becomes less obvious how to define the correct procedure that yields an unambiguous and relativistically invariant answer. Therefore, one must find a way to perform the calculation in a manner where in each step the relativistic invariance is preserved. That is, the covariance must be manifest throughout the calculation. This requirement immediately disqualifies the familiar Hamiltonian methods, because in those methods, one defines a wave function or quantum field throughout space at a fixed time, and then via the Schrödinger equation, one calculates the entire field some time later. But according to relativity, one cannot unambiguously define an entire field at one fixed time, because 2 points that are evaluated at the same time for one observer are not necessarily evaluated at the same time for another observer. So to fix the theory of quantum electrodynamics, we have to take care of two things. The first thing is to simply improve the bookkeeping. That is, we do not introduce any new physics. We work with the exact same physical theory of quantum electrodynamics that was already known, but we just perform the calculations in a different way, such that the covariance is manifest at each step. The impact of improved bookkeeping is not to be underestimated. The time required to perform a calculation could be reduced from months to weeks, and crucial mistakes can be avoided much more easily. The second step is to introduce new physics, which specifies how to remove infinities via renormalization. Without the improved bookkeeping, it could be very confusing to figure out how to correct for different infinite terms. But if you can keep track of the different terms in a relativistically invariant manner, it becomes much clearer how to correctly compensate for the infinities. Different solutions to these problems were being developed. The most famous approach, which nowadays is considered the standard, uses the diagrams that Richard Feynman introduced. His methods were so effective that other contributors to the theory of quantum electrodynamics are sometimes overlooked. However, Julian Schwinger performed highly relevant QED calculations before Feynman did, and for some time, Schwinger was in fact the more famous of the two. But even before Schwinger, there was already Tomonaga-Shinichiro. While Tomonaga was working on the problem in Japan, there was no scientific collaboration with the USA because of the Second World War. After the war, it came as a surprise that amidst the destruction, somebody was able to still do physics. It turned out that Tomonaga achieved basically the same results as Schwinger several years earlier, and in a much clearer way. So there were two different methods to solve the problems in QED, one by Schwinger and Tomonaga, the other by Feynman. The Tomonaga-Schwinger method was developed in a rather conservative manner, in the sense that it built upon the standard quantum field theory that was known at the time. Schwinger did not want to radically alter quantum field theory, and wasn't willing to abandon theoretical progress that had been hard-won. Feynman's attitude was the complete opposite. He was very much willing to challenge conventional knowledge and to develop new theories from scratch. For example, for some time, Feynman blocked his mind from learning about creation and annihilation operators, which are still standard concepts to this day. As a consequence, when Schwinger presented his new methods, he could explain it more easily because it was closer to the conventional ways of thinking. Feynman's method, on the other hand, was received differently. It was recognized that with his method, several pages of calculation can be avoided, and the result could be written down immediately. But because nobody really understood why the method works, it was called the intuitive method. It was Freeman Dyson who demonstrated how Feynman's method could be derived from the Tomonaga-Schwinger theory, thereby showing their equivalence and improving the understanding of both approaches. Dyson, too, was first bothered by Feynman's intuitive method. You would just write things straight down like magic without solving equations. The connection between the theories of Feynman and Schwinger was not obvious at all. But since Dyson had been in close contact with both of them, he had a unique opportunity to put the two together. Since Feynman's method is significantly simpler, as well as the modern standard, we will mostly focus on that approach. However, to better appreciate the context of these developments, we first sketch the line of reasoning behind the Tomonaga-Schwinger theory. To understand the origins of the Tomonaga-Schwinger theory, we recall from a previous video how Pauli and Heisenberg formulated the quantum theory of fields. Just like the electromagnetic field can be described as a system of many particles, called photons, we can describe a system of many particles, such as electrons, as fields. However, Dirac objected to this viewpoint. He argued that fields are used to observe particles, so the two play fundamentally different roles, and they cannot be put on the same footing. Instead, Dirac proposed a different way to develop the quantum theory of many particle systems. The problem that Dirac saw with the then-current theory was that at a fixed time, the states of all particles are described. This description is not in line with the spirit of relativity, because space and time play different roles here. So Dirac proposed a theory where each particle would have its own time variable. The wave function describes the probability that one particle is in a certain state at one time, and another particle is in a certain state at a different time. Because the wave function now depends on multiple time variables, this theory is referred to as the many-time theory. It turned out, however, that this new theory is formally equivalent to the quantum field theory of Heisenberg and Pauli that Dirac objected to. Pauli was very harsh and direct in his criticism of Dirac's work. He claims that Dirac's introduction was confusing and half understandable because only half understood, only to lead to a result that is identical to that of Pauli and Heisenberg, even though Dirac claimed he can construct a better theory. Tomonaga, on the other hand, was much more positive about Dirac's work, calling his philosophy much more beautiful and satisfactory than other theories. He used the idea behind the many-time theory to improve quantum field theory. While in Dirac's many-time theory each particle has its own time variable, Tomonaga proposed to assign each field point a different time. Therefore, he called this theory the super many-time theory. This was essentially the same theory that Schwinger developed independently. Now let's look in more detail at the theory of Tomonaga and Schwinger. In the non-covariant quantum theory, we consider a wave function where all points in space are evaluated at a single fixed time. This means that space and time play different roles in the description of the quantum theory, so relativistic covariance is not manifest. In the Tomonaga-Schwinger theory, we evaluate the quantum state on an arbitrary hypersurface, where both the space coordinate and the time coordinate are allowed to vary. So in this description, space and time are treated equally. Another feature of the Tomonaga-Schwinger theory is that the system is evaluated in the interaction picture. To understand what this means, consider the case where a particle is stationary. In that case, the wave function is constant in time. But when we move to a different reference frame, the particle is no longer stationary, which means the wave function is no longer constant in time. Therefore, depending on which reference frame we consider, the wave function may or may not be constant. This is undesirable, because if the covariance of the theory is to be manifest, we want the description of the system to be independent of the chosen reference frame as much as possible. Therefore, consider a system of multiple particles which are not interacting. If we move to a different reference frame, the particles are still not interacting. Therefore, if the wave function describes only the interaction between particles, then a constant wave function will be constant in all reference frames. We saw in a previous video how we can construct such a description of a system. We start with a Hamiltonian where no interaction is present between different particles. Then we add an interaction term as a perturbation to the Hamiltonian. We can define a representation of the wave function in the interaction picture, which is constant if the interaction term is set to 0. The Hamiltonian that describes the time evolution of the wave function in the interaction picture can be calculated from the non-interacting Hamiltonian and the interaction term. With this new wave function and Hamiltonian, we can write the Schrödinger equation that is valid in the interaction picture. These are therefore the key points of the Tomonaga-Schwinger theory. We evaluate the quantum state on an arbitrary hypersurface in spacetime instead of at a fixed time. And we describe the state in the interaction picture, so that the state is constant in all reference frames if there is no interaction. Let us now recall the theory of quantum fields that was discussed in a previous video. When we consider quantum fields, we don't consider a wave function, but a wave functional. This means that it takes as input not a single particle position, but an entire field configuration that extends over all space. The wave functional returns for each field configuration the probability amplitude that the system is measured to be in that configuration. The time evolution of the Schrödinger functional is described by the Schrödinger equation. In this case, the Hamiltonian is given by the integral of the Hamiltonian density. This equation describes how, if we know the wave functional at a certain time t, we can calculate what the functional looks like a short time dt later. This description is not covariant, because space and time are treated differently. Moreover, because we have to integrate the Hamiltonian density over all space, this description of the time evolution of the wave functional is not explicitly local. In the theory of Tomonaga and Schwinger, we define an arbitrary hypersurface where the time is some function of position. The Tomonaga-Schwinger equation changes the regular derivative with respect to time into a functional derivative with respect to the hypersurface. Moreover, it changes the Hamiltonian to the Hamiltonian density. With this equation, we can calculate from the wave functional on one hypersurface what the wave functional will look like on another hypersurface. Note that it is now possible to examine local deformations of the hypersurface, whereas in the original Schrödinger equation, the entire surface shifts in time. To make plausible that the Tomonaga-Schwinger equation is correct, we can demonstrate that one can derive the Schrödinger equation from it. We start by recalling the definition of the functional derivative. If we change the input function by a small difference function, then the change in the value that the functional returns is given by the integral of the functional derivative times the small difference function. We choose our initial input function to be a surface of constant time. The difference function is also constant and proportional to the small change in time dt. When we plug the Tomonaga-Schwinger equation in the definition of the functional derivative, we recover the original Schrödinger equation. We will now see more generally how we can calculate the time evolution of a wave functional using the Tomonaga-Schwinger equation. First, we consider the incremental change from some surface sigma 0 to a slightly different surface sigma 1. The wave functional at the second surface is equal to the wave functional at the first surface plus the incremental change due to the surface deformation. We substitute the functional derivative using the Tomonaga-Schwinger equation. We can write the surface deformation as the time integral bounded by the two surfaces. The integrals over space and time can be combined to an integral over four-dimensional space-time volume. This yields the expression for how the wave functional at surface sigma 0 transforms to the wave functional at a slightly deformed surface sigma 1. If we want to calculate the wave functional at some surface arbitrarily far away, then we can divide the spacetime volume in between into many thin slices. The full propagator can then be written as a sequence of many incremental propagators between the slices. We can rewrite the expression for this propagator by expanding the product. The zeroth order term is simply equal to 1. The term that is first order in the interaction Hamiltonian density is found by collecting the relevant cross terms. The sum of these cross terms can be combined into one integral, whose bounds are the initial and final hypersurface. The next term in the expression is the one that is quadratic in the interaction Hamiltonian density. After collecting the relevant cross terms, we find two double integrals. Note that for both double integrals, the lower bound of the first integral equals the upper bound of the second integral. The lower bound of the second integral is always equal to the initial surface. So if we imagine taking the limit of having infinitely many thin slices, then we can combine all these double integrals such that the first integral runs from the initial surface to the final surface, while the upper bound of the second integral is determined by the integration variable of the first integral. The expansion of this time evolution operator can be calculated to arbitrarily high orders. When we analyze scattering problems, we are interested in the time evolution operator that transforms the system from the infinite past to the infinite future. This operator can be represented as a matrix, which is known as the Heisenberg S matrix. The idea is that in the infinite past, the particles can be approximated as non-interacting. So in the interaction picture, the state vector is constant in time and well-defined in the infinite past. At some point, the particles get close to each other, and their interaction becomes non-negligible. They undergo some sort of interaction, about which the S-matrix gives no specific details, because these intermediate states cannot be measured experimentally anyways. This is consistent with Heisenberg's philosophy when he developed matrix mechanics. Quantities that are experimentally unobservable should play no role in the theory. What we observe experimentally are the particles long after they have scattered, and they are again approximately non-interacting. In the interaction picture, this is a constant state, which can therefore be described by a state in the infinite future. This is basically the degree to which Dyson summarized the theory of Tomonaga and Schwinger. The time evolution propagator can be interpreted as a sequence of propagators between the infinite number of slices. This product can be expanded to a certain order. By taking the limit to infinity, one obtains Heisenberg's S-matrix. Dyson goes a little bit further and explains that we can split the interaction term in interaction between the particles themselves and interaction with an external field. From this, we can obtain a complicated expression that leads to a long and difficult analysis. Schwinger performed this analysis to demonstrate agreement with experiment, but we will conclude the summary of the Tomonaga-Schwinger theory here. We will now discuss Feynman's approach to quantum electrodynamics. To understand his line of reasoning, we will go through 5 of his papers. The first paper is about classical electrodynamics. In a previous video, we saw that already in the classical theory, there were problems with the diverging mass and self-energy for a point electron. Since the discovery of quantum mechanics revealed that classical theory is inaccurate, there was not much interest in trying to fix these divergences in classical theory. It made more sense to find a more accurate quantum theory of electrodynamics and hope that such a theory would automatically fix these problems. However, this did not turn out to be the case. Also in quantum electrodynamics, the problem of divergences was still present. Therefore, Feynman's plan was to go back to the classical problem, fix the divergences there, and then turn it into a quantum theory where there would be no more problems anymore. He had the following idea. The problem is that the electric field as described by Coulomb's law diverges at the position of the electron. Therefore, if a point electron interacts with its own field, it results in a diverging energy. So let's just get rid of the notion of an electric field. Let's instead think in terms of action at a distance. That is, if you move an electron at one position, then after some delay, another electron feels its effect, without specifying any sort of field in between. The only way an electron can act on itself is via the delayed interaction with a second electron. But this gives a problem. We know that an electron can act on itself via radiation reaction. This effect is measurable, and it is instantaneous instead of delayed. So how can Feynman's theory of action at a distance without fields account for this? It was proposed to include in the theory the interaction via advanced waves. These waves are emitted by the second electron before any wave was emitted by the first electron. In other words, the effect happens before the cause. These advanced waves are mathematically speaking a valid solution to Maxwell's equations, but they are typically ignored because they seem unphysical. There cannot be an effect before a cause. However, there were already plenty of concepts in physics that are counterintuitive yet widely accepted, such as Einstein's special relativity or the uncertainty principle in quantum mechanics. Therefore, Feynman wasn't too much bothered by the idea of advanced waves, no matter how paradoxical it seems at first sight. So that was one way Feynman tried to fix classical electrodynamics, by describing the interaction between electrons as action at a distance without fields, and postulating that an electron cannot act on itself. But this is not the only way one can solve the problem of diverging self-energies. There are different ways in which one can modify classical electrodynamics, and it was not obvious which way is correct. So Feynman also considered a different modification of the classical theory. The second way to remove the divergences is to still allow for the electron to interact with itself, but to modify the form of the interaction. In other words, one postulates that Coulomb's law is not valid very close to the electron. We will now discuss this second way to modify classical electrodynamics. We start with the expression for the retarded potential. This expression uses the forecurrent and the forepotential. It includes both Coulomb's law, which describes how a charge distribution generates a scalar potential, and the Biot-Savart law, which describes how a current distribution generates a magnetic field. It says that the effect of the forecurrent propagates at the speed of light. That is, the forepotential at some location and some time depends on the forecurrent at a different location some time ago. This time in the past is also called the retarded time. We now rewrite the expression for the forecurrent evaluated at the retarded time. We write it as an integral over time, where the integrand is non-zero only if the time is equal to the retarded time. Using this expression, we can write the forepotential as an integral over both space and time. This is the expression for the retarded potential. But recall that Feynman proposed to also include advanced waves, so that the potential depends not only on currents in the past, but also currents in the future. Therefore, we add an extra delta function that selects a time in the future. We can simplify this expression by rewriting the delta function. If we multiply the argument of the delta function by some constant a, then we get the same result as dividing the delta function by the modulus of a. Now suppose the argument of the delta function is the product of two functions f and g, which are equal to 0 for different values of x. Then the delta function is non-zero either when f equals 0 or when g equals 0. When f equals 0, the delta function has to be divided by g, and when g equals 0, the delta function has to be divided by f. Now let's consider a delta function whose argument is position squared minus time squared. We can factorize this expression so that the argument of the delta function is the product of two functions. By using the formula we just found, we can write this delta function as the sum of two separate delta functions. We can evaluate the denominators at the time t, where the delta function in the numerator is non-zero, because that's the only case where the value of the denominator is relevant. When we write the two terms as a single fraction, we find the same expression that occurs in the formula for the forepotential. Therefore, we can simplify this formula by substituting our result. From special relativity, we recognize the argument of the delta function to be the spacetime interval between 2 points in spacetime. Therefore, the forecurrent at one point in spacetime only contributes to the forepotential at another point in spacetime if the spacetime interval equals 0. We can visually represent this in a spacetime diagram as follows. If at the origin we consider the point where we evaluate the forepotential, then only the forecurrent that lies on the light cone contributes to that point. Since Feynman introduced the contribution of advanced waves, both times in the future and the past can contribute to the forepotential in the present. The modification to classical electrodynamics that Feynman proposed is to substitute the delta function with a sharply peaked function of finite width. This means that the forecurrent doesn't have to lie exactly on the light cone to contribute to the forepotential. By applying this modification, the problem of infinite self-force, self-energy, and electromagnetic mass is eliminated. It means that Maxwell's equations are no longer satisfied exactly, but this violation is only significant over extremely small distances from the electron. At such small distances, we cannot experimentally verify Maxwell's equations anyway. For larger distances where we are able to perform reliable measurements, this modified theory is consistent with observations. So now we know how Feynman modified the classical theory of electrodynamics in the spacetime domain. However, very often we analyze systems in the Fourier domain. That is, we decompose quantities in plane waves, each with their own wave vector, or momentum, and angular frequency, or energy. What impact does Feynman's modification have in the Fourier domain? In the unmodified Maxwell theory, the field can be decomposed in plane waves, which must satisfy the dispersion relation. That is, the length of the wave vector fixes the angular frequency. Feynman's modification of the interaction at small distances implies that the Fourier components of the field no longer satisfy the dispersion relation exactly. The final important point that Feynman addresses in his paper is the interpretation of electrons traveling backward in time. When Feynman described the interaction between electrons as action at a distance instead of through fields, he could no longer use Hamiltonian methods to describe the dynamics. This is because the Hamiltonian method is used to calculate time derivatives, so that the current state determines how the state evolves. But if one removes the concept of fields and substitute them with delayed interactions, the evolution of the state is no longer determined by only the current state of the system, but also by past states. And if one considers advanced waves, also by future states. In that case, one can still describe the system dynamics using the principle of least action. If one does so, we may find solutions where an electron travels backward in time. It is proposed that such an electron can be interpreted as a positron. To see how this works, we apply the principle of least action to a toy problem where a particle travels from one point in spacetime to another point. The path that the particle follows is one whose action is stationary. Now suppose that to define the particle's path, there are two positions where we must define the times that the particle passes through them. Physically, this only makes sense when there is some potential barrier, because otherwise the particle always just goes straight from point 1 to point 2. But we can simplify the calculation and still demonstrate our point if we ignore this change in potential. Moreover, let's assume that the distances between the three positions are the same and equal to 1. To calculate the action, we observe that the action integral can be written as a sum over the three sections, and the Lagrangian reduces to the kinetic energy in the absence of a potential. For the first section, we can calculate the contribution to the action by multiplying the kinetic energy with the time interval. Similarly, we can calculate the contribution from the second section and from the third section. We can simplify the terms and collect them to find the final expression for the action. To find the path that the particle will take, we find the extrema of the action. This means that we must take the derivatives of the action with respect to the free parameters and set these derivatives equal to 0. We can calculate these two derivatives, set them equal to 0, and then solve the two equations. Note that each equation has two solutions because of the squares. Therefore, we have a total of 4 solutions for the path that the particle can take. By choosing a certain sign for the first equation and a certain sign for the second equation, we can solve for the times t3 and t4. We can do this for all the 4 combinations of the signs. Now let's plot the 4 solutions to see what they look like. The first solution is the obvious one. The particle goes straight from point 1 to point 2. In the second solution, the particle first goes forward in time, but in the last part it goes backward in time. In the third solution, the particle first goes backward in time and then forward. And in the fourth solution, the particle first goes forward in time, then backward, then forward again. So how do we interpret the regions where the particle goes backward in time? Recall that we defined the action integral such that we go from time t3 to t4. When t4 is smaller than t3, it means we go backward in time. To go forward in time again, we must switch the integration limits, but then we must also introduce a minus sign to maintain equality. Therefore, a particle with positive energy going backward in time can be interpreted as a particle with negative energy going forward in time. In Dirac's theory, these negative energy states correspond to antiparticles. So an electron going backwards in time is interpreted as a positron going forward in time. So this is what the four solutions represent. In the first solution, the electron moves from left to right in a certain amount of time. In the second solution, we have an electron and a positron that move towards each other and eventually annihilate. In the third solution, an electron-positron pair is created and the two particles move in opposite directions. In the fourth solution, we have an electron at one point, while an electron-positron pair is created at another point. The first electron annihilates with the positron, while the second electron moves away freely. This concludes the discussion of Feynman's first paper. To remove the divergences occurring in classical electrodynamics, Feynman proposed to no longer think in terms of fields, but in terms of action at a distance. Moreover, he described a method to modify the short-distance interaction between electrons, and he explained how electrons traveling backward in time can be interpreted as positrons. Now that we have examined Feynman's ideas regarding classical electrodynamics, we proceed to his second paper where some of these ideas are applied to quantum electrodynamics. The main focus of this paper is to demonstrate how Feynman's modification of the short-distance interaction, and therefore the photon dispersion relation, can be used to calculate a finite self-energy and the Lamb shift. The way that the dispersion relation is modified is described by some function g of lambda. To calculate the self-energy and the Lamb shift, Feynman uses the same second-order perturbation theory that we discussed in the previous video. In this method, the perturbation to the energy is found by considering all the transitions to intermediate virtual states. We recognize in the denominator of Feynman's expression the energy difference between the initial state and the intermediate state. The interaction Hamiltonian that is used is the one that follows from the Dirac equation in the presence of an electromagnetic field. Note that this perturbation theory is not yet the manifestly covariant one that we are looking for. In the transitions to the virtual states, momentum is conserved, while energy is not. Since momentum is related to spatial derivatives, and energy to the time derivative, space and time are not treated equally in this theory. After performing the calculation, Feynman found that the self-energy, which results in an electromagnetic mass, is given by a finite value, which depends on the specific way in which the dispersion relation is modified. This electromagnetic mass is not observable by itself, but only the sum with the electron's intrinsic mass can be measured experimentally. In the limit where the dispersion relation is as in conventional electrodynamics, the self-energy diverges logarithmically, as we saw in the previous video on Weisskopf's calculation. To calculate the Lamb shift, one has to apply mass renormalization, which means one has to subtract the self-energy of a free electron from the total energy of the bound electron. The novelty that Feynman proposes is to perform this procedure with the modified dispersion relation, so that at all times one calculates with finite quantities. In the end, it is found that the calculated Lamb shift does not depend significantly on the specific form of the modification. Therefore, the function g of lambda that describes the modification is only a bookkeeping device to help perform the calculation. It appears only as a complicated scaffold which is removed after the calculation is done. Finally, Feynman notes that in addition to the problem of self-energy, which is solved by mass renormalization, there is also the problem of vacuum polarization, which is solved by charge renormalization. The diverging self-energy is caused by the electron emitting and reabsorbing photons. Therefore, in Feynman's approach, it is addressed by modifying the dispersion relation of the photons. Vacuum polarization is caused by the electron field creating electron-positron pairs, which later annihilate with each other. Therefore, this divergence is addressed by modifying the dispersion relation of the electrons. So we saw that in this paper, Feynman addressed the divergences in quantum electrodynamics by modifying the short-range Coulomb interaction, which is equivalent to modifying the photon dispersion relation. However, the perturbation theory that was used to calculate the self-energy and the Lamb shift was still the old theory, which is not manifestly covariant. In Feynman's next paper, he further elaborates on his theory where he removes fields and substitutes them with action at a distance. In the first paper that we discussed, we saw how he applied this idea to classical electrodynamics. The next thing that needs to be done is to turn this into a quantum mechanical theory. The problem is that up to that point, whenever we wanted to turn a classical theory into a quantum theory, it had to be done in the Hamiltonian framework. But this Hamiltonian can only be constructed if the Lagrangian is a function of a single point in time. When we remove fields, and instead think in terms of action at a distance, the Lagrangian will be a function of different points in time, and then it is not obvious how this theory can be made quantum mechanical. Feynman was struggling with this problem, and when he asked for help, he was pointed to a paper of Dirac. In his paper, Dirac notes that quantum mechanics was built on Hamiltonian theory, but there is also the Lagrangian theory, which arguably could be considered more fundamental. One reason for this is that the Hamiltonian method is essentially non-relativistic, because it evaluates a wave function at different locations in space at the same point in time. In contrast, the action that is used in the Lagrangian theory is a relativistic invariant. And this is exactly what was needed in the development of quantum electrodynamics, a manifestly covariant formulation of the theory. The action already played an important role in the development of the Schrödinger equation. The phase of the wave function was assumed to be proportional to the action. Dirac further extended this connection, and in that way he formulated a quantum analog of the action principle. Feynman didn't find this very useful. What exactly does it mean when two quantities are analogous? What's the use of that? So he did a quick blackboard calculation and found that the two quantities that were supposed to be analogous are in fact proportional. With that, Feynman found the connection between the Lagrangian and quantum mechanics that he needed, and this he published in the third paper that we will now discuss. The key equation in this paper is the one where the evolution of the wave function is described in terms of the action. Our goal is to demonstrate that this is equivalent to the Schrödinger equation. In this equation, we start with the wave function at a fixed point in time, evaluated at all points in space. From this, we calculate the wave function a small time interval epsilon later. Each point of the initial wave can be thought of as emitting rays with a complex phase that is proportional to the action. Therefore, to calculate the wave function at a certain point sometime later, we have to add the rays from all the points of the initial wave function. To see how we can derive the Schrödinger equation from this, we start by calculating the action. If the small separation in time is given by epsilon, and we consider a ray that travels a small distance psi, then we can approximately calculate the action as the kinetic energy minus the potential energy times the time interval epsilon. This product can be expanded straightforwardly. The value of the wave function at the initial position and initial time can be approximated with a second-order Taylor expansion in the position coordinates. The value of the wave function at the final position and final time can be approximated with a first-order Taylor expansion in the time coordinates. We will now consider Feynman's formula that describes the time evolution in terms of the action, and we will demonstrate that it is equivalent to the Schrödinger equation. We plug in the second-order Taylor expansion of the wave function, and we plug in the expression for the action. This yields three integrals, whose values can be calculated analytically. When we collect the terms, we find an expression from which we can determine the value of the constant a. This value is chosen so that the equation is valid in the limit where epsilon goes to 0. The resulting expression we can rewrite further by plugging in the first-order Taylor expansions for the wave function and the complex exponential that contains the potential. If we expand the product on the right-hand side of the equation and only keep the terms that are linear in epsilon, we recover the Schrödinger equation. We have thus demonstrated how the time evolution of the wave function can be described in terms of the action. This description of wave propagation can be interpreted as Huygens principle. Each point acts like a point source emitting a spherical wave. The propagated wave is found by summing the spherical waves of all points. This is how we can propagate the wave function to an infinitesimal time interval epsilon later. If we want to calculate the wave function at some arbitrary time, we find that we must sum over all the paths that we can define between the initial and final points. We saw how the non-relativistic Schrödinger equation that uses the Hamiltonian can be reformulated by using the Lagrangian and action. In Feynman's next paper, we will see how we can include positrons in the theory as required by relativistic quantum mechanics. We saw how the time evolution of the wave function can be interpreted as each point in the initial wave function giving its own contribution to the final wave function. This contribution can be described with a function called the kernel. This kernel is a function of the initial point in spacetime and the final point in spacetime. To find the wave function at the final point, we sum the contributions from all the initial points. We will now find the conditions that such a kernel must satisfy. First, we consider the special case where the final time equals the initial time. In that case, if we want to describe the wave function as itself convolved with some function, we find that this function has to be the delta function. Therefore, the kernel must satisfy the boundary condition that at the initial time it must be a delta function in space. To find the kernel for other times, we consider the Schrödinger equation. We write the wave function as the integral over the kernel. Since the operators in the Schrödinger equation depend only on the unprimed coordinates, we can pull them inside of the integral, which is over the primed coordinates. Since the integral must be 0 for any initial wave function, the integrand must be 0, and the kernel must satisfy the Schrödinger equation. So we found the conditions that the kernel must satisfy. From the kernel, we can define another function, called the Green's function, by multiplying the kernel with the Heaviside step function. This step function equals 1 if the final time is later than the initial time, and 0 otherwise. Therefore, the kernel is modified such that the wave function at some point can only affect the wave function in the future, not in the past. Now consider what happens when we plug in this Green's function in the Schrödinger equation. For times larger than the initial time, the equation is unmodified, so it still holds. For times smaller than the initial time, the Green's function is 0, so the equation also still holds. The only point where the equality of the Schrödinger equation is violated is when the time is exactly equal to the initial time. There, the Heaviside step function introduces a discontinuity, and taking the time derivative yields a delta function in time. This delta function is multiplied with the kernel, evaluated at the time where the delta function is non-zero. We established that in this case, the kernel is a delta function in space. Therefore, the Green's function satisfies the Schrödinger equation, except the right-hand side is set equal to a four-dimensional delta function. Note that the Green's function does not uniquely follow from this equation. One can add any solution of the homogeneous Schrödinger equation to a Green's function and obtain another valid Green's function. The reason why Green's functions are important is because they help solve inhomogeneous differential equations. Suppose we want to solve the Schrödinger equation where the right-hand side is set equal to some arbitrary source term. To find the solution, consider the Green's function equation multiplied with the source term and integrated over spacetime. The right-hand side reduces to rho because of the delta function. On the left-hand side, we can take the operators of the Schrödinger equation outside of the integral, since it doesn't depend on the integration variables. When we compare the resulting expression to the initial equation, we find that the solution to the initial equation is given by convolving the source term with the Green's function. That is, each point in the source term can be interpreted as a point source emitting a Green's function. So we now know how we can solve the inhomogeneous Schrödinger equation by using a Green's function. This method works when the source term is a known function. That is, it cannot depend on the unknown wave function. However, we typically cannot make this assumption. In a typical problem, we have an unperturbed Hamiltonian for which we can solve the Schrödinger equation, and then we apply a perturbation to the Hamiltonian. When we rewrite this equation, we find that the source term depends on the unknown wave function. If we then write down the solution using the Green's function, the wave function occurs on both sides of the equation, so it is not straightforward to calculate the wave function. One way to find approximate solutions is via the Born series. In this method, we start with a known solution to the homogeneous Schrödinger equation. This wave function is the incident field that will be scattered by the perturbing Hamiltonian. To a zeroth order approximation, if the scattering is very weak, we can assume that the wave function is practically unaffected by the perturbation. In other words, in this approximation, the scattering is negligible. In the first order approximation, we plug in the incident field in the Green's function solution. That is, we assume that only the incident field itself is scattered by the perturbation, and the scattered field is not scattered again. We therefore can call this the single scattering approximation, and we can add this scattered field to the unscattered incident field to find a better approximation of the wave function. But now that we have a more accurate approximation of the wave function, we can again plug this into the Green's function solution to get an even better approximation. That is, we now also calculate how the scattered field is scattered again by the perturbation. Therefore, we can call this the double scattering approximation. We can add this to our expression for the total wave function, and we see how we can continue this sequence to get increasingly more accurate approximations, assuming that the terms do not diverge. We can visualize these first and second order approximations as follows. In the single scattering approximation, the incident field is scattered once by the perturbing Hamiltonian, and it can be scattered at any point in spacetime. We have to sum over all these scattering locations and times to find the total scattered field. In the double scattering approximation, the field scatters twice before reaching the endpoint. To find the total double scattered field, we need to sum over all possible pairs of points in spacetime. We can see the connection with Feynman's idea of summing over all possible paths to find the wave function at the final point. So we saw how we can use the kernel to calculate the free propagation of the wave function, and how from the kernel we can find a Green's function which can be used to calculate how the wave function is scattered by a perturbation. However, we didn't yet calculate the kernel. This is what we will do now. First, we assume we know the eigenvectors and eigenvalues of the Hamiltonian. These correspond to the states of definite energy. From these time-independent eigenstates, we can calculate the time-dependent states. The eigenstates form an orthonormal basis, so we can write any arbitrary wave function as a linear combination of these eigenstates. We can do this for the final time and the initial time. The coefficients for these decompositions are the same, only the time is different. Therefore, we can calculate the coefficients from the wave function at the initial time by taking the inner product with the eigenstates, and then we can plug these coefficients in the expression for the wave function at the final time. We have now expressed the wave function at the final time in terms of the wave function at the initial time, and from this we can directly read the expression for the kernel. Note that to define this kernel, we summed over all energies. That is, both positive and negative energies are included in the sum, and therefore the Green's function that we found by multiplying the kernel with the Heaviside step function also includes both positive and negative energies. However, according to positron theory, when an electron propagates, it only has access to the positive energy levels. The negative energy levels are already occupied by the Dirac sea, and by the Pauli exclusion principle, these states cannot also be occupied by another electron. Therefore, to find a Green's function that is consistent with positron theory, we should define it such that it only contains positive energy states. Recall that this is possible because the Green's function is a solution to an inhomogeneous differential equation, so we are free to add any homogeneous solution to the Green's function to find another valid Green's function. Therefore, we consider a homogeneous solution that is a linear combination of all negative energy states. Because each energy state is a homogeneous solution to the Schrödinger equation, so is any linear combination of them. When we subtract this homogeneous solution from our Green's function, we obtain the desired results for times later than the initial time. The Green's function there consists only of positive energy states. However, for times earlier than the initial time, we find the negative sum over all negative energy states. This Green's function is known as the Feynman propagator. We can physically interpret it as follows. From the expression for the second-order Born approximation, we saw that we must sum over all paths from the initial to the final point where the electron is scattered twice. In some paths, the electron goes only forward in time. For those paths, the Feynman propagator tells us it only occupies positive energy states, so the particle is a regular electron. However, for other paths, there are regions where the electron goes backward in time. According to the Feynman propagator, for these regions only negative energy states are occupied, so then the electron is to be interpreted as a positron. Therefore, by defining the Green's function in this manner, we have reproduced the result that Feynman proposed in his first paper based on classical grounds. When we consider all paths in spacetime, an electron propagating backwards in time is to be interpreted physically as a positron propagating forward in time. So we see how with Feynman's choice of the Green's function, we can elegantly and efficiently account for pair production and annihilation. There is one further subtlety that needs to be addressed, which is related to the exclusion principle. When we blindly sum over all possible paths in spacetime, we will be including paths where, due to pair production, two electrons with the same momentum will occupy the same position at the same time. The exclusion principle forbids this. So, should we take special care to avoid this scenario when we sum over all paths? Feynman answered that question as follows. We can physically observe only changes with respect to the vacuum state. In other words, we should consider all events with an electron present and all vacuum events without an electron present, and then take the difference of those to calculate a physical quantity. One such process that can take place in vacuum is one where an electron-positron pair is created and sometime later the same pair annihilates. When we add an electron to the vacuum, we add all the physically allowed paths the electron can take from the initial point to the final point. We should not include paths that violate the exclusion principle. But by introducing the electron, vacuum processes where pairs are produced and annihilated become forbidden because an electron-positron pair cannot be produced where there's already an electron present. So when we take the difference between all single electron processes and all vacuum processes, we see that we might as well ignore the exclusion principle in the intermediate states. We will now apply these results to the Dirac equation, and we will introduce the momentum representation as this will simplify the analyses. We start with the equation for the Green's function, and then plug in the Hamiltonian corresponding to the Dirac equation. Note that the delta function on the right-hand side is now multiplied with a four-dimensional identity matrix, since the Dirac equation is actually four equations written as one. We can rewrite this equation using covariant notation. Here we assume that the Green's function depends only on the difference between the initial and final points, not on the absolute position and time. To go to the momentum representation, we write the Green's function as a linear combination of momentum eigenstates. We plug this into the Green's function equation, where we also expand the delta function in momentum eigenstates. Taking the four-gradient of the momentum eigenstates yields the four momentum. The product of a four-vector with the vector of gamma matrices can be abbreviated using Feynman's slash notation. When we equate the integrands of both sides of the equation, we find the Green's function equation in the momentum representation. From this equation, we can solve for the Green's function in the momentum representation. In this expression, the division denotes the inverse of a four-dimensional matrix. We multiply this expression by 1 and then multiply the two fractions to obtain a result where the denominator is a simple scalar instead of a matrix. This scalar involves the squared length of the four momentum, which consists of the energy and the regular momentum. We observe that the denominator becomes 0 when the relativistic energy-momentum relation of a particle holds. The fact that we divide by 0 indicates that the Green's function is ill-defined. This is directly tied to the observation that in position space, we could add to the Green's function any homogeneous solution and get another valid Green's function. In the following, we will see exactly how the ambiguity arises from the poles and how we can resolve the ambiguity. To see how the poles cause ambiguity, let's for the sake of simplicity focus only on the denominator, while setting the numerator equal to 1. Physically, this corresponds to examining the Green's function of the Klein-Gordon equation instead of the Dirac equation. We can write this fraction as the sum of two fractions, where each fraction carries one pole. When we plot this function, we see that at each pole, the function goes to positive infinity at one side and to negative infinity at the other side. So if we integrate around the pole to find the Green's function in position space, the result is undefined, because basically you would subtract infinity from infinity, which can yield any value depending on how you take the limits. For example, consider the case where we integrate around the pole with symmetric boundaries and with asymmetric boundaries. In both cases, the boundaries go to 0, but because of how exactly we take the limits, we get different outcomes. In the first case, the limit yields 0, because due to symmetry of the boundaries, we integrate over as much positive value as over negative value. In the second case, we get a non-zero value because due to the asymmetric boundaries, we integrate over more positive values than over negative values. Therefore, when integrating over a pole, we need to carefully define how we take the limit. Taking the principal value of an integral means that we define the boundaries symmetrically around the pole. To see how we can resolve the ambiguity introduced by the poles, we first simplify the problem as much as possible to reduce it to its core essence. We started with the Green's function for the Dirac equation in the momentum representation. Since the problem arises when we divide by 0, we focus only on the denominator and set the numerator equal to 1. Moreover, we write the four-dimensional integral as an integral over energy and an integral over three-dimensional momentum. To capture the essence of the problem, we only need to focus on one pole and integrate over energy only while keeping the momentum fixed. We can simplify notation, and we can shift the function so that the pole lies at 0. Now that we have simplified the problem to its core essence, we will see how we can resolve the ambiguity. We add a very small imaginary number to the denominator to avoid division by 0, and then let the small number go to 0. To see what this does, we separate the fraction in its real part and imaginary part. We do this by multiplying by 1 and then expanding the product. First we consider the real part and plug it into the integral. The first term is an odd function, so it integrates to 0. The second term reduces to a sinc function when we let epsilon go to 0. The width of the sinc function is inversely proportional to its height, so that the area remains constant. However, if we change the sign of the scaling factor, the integral becomes negative. Therefore, the integral is proportional to the signum function. Now that we have evaluated the real part, we move on to the imaginary part. In case omega is non-zero, we can let epsilon go to 0 with no problem and find that the expression reduces to 0. However, if omega is 0, the expression reduces to 1 over epsilon, which goes to infinity when epsilon goes to 0. This has the structure of a delta peak, which also has a sharp infinite peak at 0 and vanishes everywhere else. To determine the height of the delta peak, we observe that for every positive value of epsilon, the total area is equal to pi. Therefore, we find that in the limit where epsilon goes to 0, the expression reduces to pi times the delta function. Plugging this result in the integral yields a value of pi. We thus find that the integral of the real part of the fraction yields pi times the signum function, while the integral over the imaginary part yields pi. This result is basically a consequence of the Souchotsky-Plamel formula, which expresses the limit of the fraction as a principal value and a delta function. When we add the results of the real and imaginary part together, we obtain something proportional to the signum function plus 1. When we plot the signum function and shift it up by 1, we see that we obtain a Heaviside step function. Therefore, this Green's function expresses a causal response. The impulse response of the system follows only after the impulse has been applied. If instead of adding a small imaginary number to the denominator, we subtract a small imaginary number, we find a step function that is non-zero for times in the past and 0 for times in the future. That is, we have an advanced Green's function, where the system feels the impulse response before the impulse has been applied. So depending on whether we add or subtract a small imaginary number in the denominator, we obtain either a retarded or advanced Green's function. Recall that in the Green's function for the Dirac equation or Klein-Gordon equation, we have two poles, corresponding to the positive and negative energies. According to Feynman, the positive energies correspond to electrons which travel forward in time, so this pole should yield a retarded Green's function. The negative energies correspond to positrons, which travel backward in time, so that pole should yield an advanced Green's function. Therefore, we add and subtract a small imaginary number in the two denominators. We can write the two fractions as a single fraction. In the numerator, we let epsilon go to 0, and we expand the product in the denominator. We ignore the term that is quadratic in epsilon, and the term that is linear in epsilon we write more compactly by defining a new epsilon, which is valid because both epsilons should go to 0 anyway. We have now found an expression that satisfies the requirements of the Feynman propagator. So to summarize, we found the Green's function of the Dirac equation in the momentum representation. The presence of zeros in the denominator indicates that the Green's function is not uniquely defined. By adding a small imaginary number to the denominator, we specify how we should integrate over the poles, so that the ambiguity is resolved. By choosing this particular form of regularization, we obtain the Feynman propagator, where positive energy particles move forward in time and negative energy particles go backward in time. The final result that we will discuss from Feynman's fourth paper is the conservation of form momentum during a scattering event. We can describe a single scattering event using the first Born approximation. To express this formula in the momentum representation, we write down the Fourier decomposition of the scattering potential. We assume that the incident wave function is a plane wave with a certain momentum, and we write down the Fourier decomposition of the Green's function. We plug these expressions in the first Born approximation, where we also decompose the scattered wave function in momentum states. When we collect the complex exponentials and integrate over space, we obtain a delta function. This delta function enforces that the momentum that is transferred by the scattering potential equals the momentum of the scattered wave minus the momentum of the incident wave. We thus find that the sum of the ingoing form momenta must equal the outgoing form momentum. Conservation of form momentum means conservation of both energy and ordinary momentum. This stands in contrast to the old perturbation theory, where in the intermediate virtual states, ordinary momentum is conserved, but energy is not. We will now move on to the fifth paper, where Feynman diagrams and the Feynman rules are introduced. Let's consider again the first Born approximation and its representation in momentum space. We will see how the interaction Hamiltonian for electrodynamics motivates the introduction of the photon propagator. We saw in a previous video that in the Lorentz gauge, the force potential satisfies the wave equation, where the force current is the source term. This is a reformulation of Maxwell's equations. We will use this result, except we set the source term equal to the delta function. Physically, this means that we calculate the force potential that is generated by a point charge. Mathematically, it means we are solving for a Green's function. Just like the Green's function for the Dirac equation is the electron propagator, the Green's function for the electromagnetic field is the photon propagator. To see how this Green's function relates to the interaction Hamiltonian, we recall how the Dirac equation is modified in the presence of an electromagnetic field. The interaction with the electromagnetic field is found by subtracting the force potential from the force momentum. When we apply this substitution to the Dirac equation, we find the expression for the interaction Hamiltonian. To relate the force vector with lower index to the force vector with raised index that occurs in Maxwell's equations, we use the metric tensor. This yields an expression for the interaction Hamiltonian that is used in Born's single scattering approximation. We will now investigate what this interaction term looks like in case the force potential is generated by a point charge. To do this, we consider Maxwell's equation, where the source term is set to a delta function. So equivalently, we are finding the Green's function for the wave equation. We will express the Green's function in the momentum representation, so we write it as a linear combination of momentum eigenstates. Here we introduce the momentum force vector, where the energy is expressed in terms of angular frequency, and the momentum is expressed in terms of the wave vector. We take the product with the position force vector to obtain a momentum eigenstate. We now plug this expression in the equation for the Green's function, and we also expand the delta function in momentum eigenstates. By setting the Fourier coefficients equal to each other, we find an expression for the photon propagator. Note that we introduce a small imaginary number in the denominator, just like we did for the electron propagator. We can now plug this expression into the perturbed Dirac equation to find the electromagnetic interaction with a point charge. When we plug this interaction Hamiltonian in Born's single scattering equation, we identify one factor as the photon propagator, and the other term is set to account for vertex interactions, for reasons which will become apparent in a moment. The constant factor in front of this expression is merely a consequence of how we chose to define our Fourier transform, so we will not pay much attention to it. We saw earlier that the Green's function in this expression is given by the electron propagator. We will now see how these results can be used to understand Feynman diagrams. As a first example, we consider Feynman diagrams that describe the process of Baba scattering. In Baba scattering, we start with an incoming electron and positron. Recall that positrons can be represented as electrons traveling backwards in time, so that's why the arrows for the positron and electron point in opposite directions, even though they are both incoming particles. After the scattering, we again have an outgoing electron and positron, but now with possibly different energies and momenta. What happens during the scattering interaction is not experimentally observable, but we saw that via the Born series we can approximate the interaction as the sum of all possible single scattering events, double scattering events, and so forth up to arbitrarily high orders. Different Feynman diagrams can be used to represent different such scattering events. Let's draw one Feynman diagram that results in Baba scattering. In this diagram, the incoming electron and positron annihilate to emit a photon. Sometime later, this photon creates an electron-positron pair, with energies and momenta that can be different from the incoming particles. To calculate the matrix element which describes the probability amplitude that such a scattering event occurs, we use the results we derived previously. When the incoming positron and electron meet at the vertex, their interaction is described by the vertex interaction term. The electron has a certain form momentum p and is described by the spinor u. The positron has some other form momentum q and is described by the spinor v. Following the direction of the arrows, we start with the electron spinor, multiply with the vertex vector, and multiply with the Dirac adjoint of the positron spinor. Out of the vertex comes also a photon that propagates to the next vertex. The form momentum of the photon is found via conservation of form momentum at the vertex. The incoming electron and positron have form momenta p and q, so the form momentum of the outgoing photon is the sum of the two. This photon comes in at the second vertex, where the positron and electron come out. Following the direction of the arrows, we start with the positron spinor, multiply with the vertex vector, and then multiply with the Dirac adjoint of the electron spinor. That is one way that an incoming positron and electron with certain form momenta can be scattered into an outgoing positron and electron with different form momenta. But the same outcome can also be achieved in a different manner, such as via the exchange of a photon between the electron and positron. In the first vertex, we again follow the direction of the arrows and write the spinor of the incoming electron, multiply with the vertex vector, and then multiply with the Dirac adjoint of the outgoing electron. Out of the vertex comes a photon that propagates to the next vertex. Via conservation of form momentum at the vertex, we find that the photon form momentum is given by the form momentum of the incoming electron minus the form momentum of the outgoing electron. At the second vertex, we follow the direction of the arrows and write down the spinor of the outgoing positron, multiply with the vertex vector, and multiply with the Dirac adjoint of the incoming positron. Therefore, we have two different diagrams that both contribute to the same scattering process, and we use the Feynman rules to calculate the matrix element. Another scattering process that we can analyze with Feynman diagrams is Compton scattering. In this process, an incoming photon scatters from an electron, after which the form momenta of the photon and electron are changed. One way to obtain this outcome is to have the electron absorb the incoming photon and then emit a photon with a different form momentum sometime later. To calculate the corresponding matrix element, we start with the incoming electron spinor and photon polarization vector. We multiply it with the vertex vector, and out of the vertex comes an electron that propagates to the next vertex. Due to conservation of form momentum at the vertex, the form momentum of the intermediate electron is given by the sum of the form momenta of the incoming electron and photon. At the second vertex, we multiply the propagator of the incoming intermediate photon with the vertex vector, and then multiply the conjugate of the outgoing photon polarization vector and the Dirac adjoint of the outgoing electron spinor. Recall that multiplying a 4 vector with the vector of gamma matrices can be abbreviated using Feynman slash notation. We will now consider a different process that results in the same outcome of content scattering. First note that we can interchange the outgoing photon and the outgoing electron. This is just a different visual representation of the same physical situation. What can happen is that the incoming electron first emits the outgoing photon and later absorbs the incoming photon. The corresponding matrix element is found by multiplying the incoming electron spinor with the vertex vector and the conjugate of the outgoing photon polarization vector. The latter two can be combined using Feynman slash notation. Also coming out of the vertex is an intermediate electron that propagates to the next vertex. Its form momentum is given by the form momentum of the incoming electron minus the form momentum of the outgoing photon. At the second vertex, the incoming photon polarization vector is multiplied with the vertex vector, and then multiplied with the direct adjoint of the outgoing electron spinor. These two diagrams both contribute to the probability amplitude of a Compton scattering process. In his paper, Feynman also analyzed Compton scattering with two diagrams, where in the first diagram a photon is first absorbed then emitted, while in the second diagram a photon is first emitted and then another absorbed. However, when we compare these two diagrams to the ones that we analyzed, they don't look quite the same at first sight. Only when we rotate the diagrams does the equivalence become apparent. This goes to show that the same physical process can be visualized in different ways, and there is no single unique way to construct the right Feynman diagram. For example, in the second diagram, we drew the internal electron slightly at an angle to indicate that it takes a finite amount of time to propagate from one position to another. But we might as well draw it straight up to make the diagram look more similar to the first. When we apply the Feynman rules, we obtain the same formula either way. Moreover, we can interchange the outgoing electron and photon in the diagram. This doesn't change the physics at all. Or we can completely rearrange all the lines as long as we have an incoming electron and photon and an outgoing electron and photon. So we find that the same two Feynman diagrams that describe Compton scattering can visually be represented in seemingly completely different ways. The diagrams that we have seen so far have a special property, namely that once the momenta of the external lines have been set, the momentum of the internal line is automatically fixed by momentum conservation. Diagrams that satisfy this property are called tree-level diagrams. There are also diagrams where this is not the case. For example, consider the diagram that depicts an electron interacting with itself. The electron emits a photon and then absorbs the same photon. This process is responsible for the self-energy of an electron. The momentum of the photon is completely independent of the momentum of the external electron line. Therefore, we must integrate over all photon momenta, and this causes the electron self-energy to be divergent. Such a diagram where one loop is present is called a one-loop level diagram. There can also be two loops in the diagram, which would be a two-loop level diagram, and so forth. Another example of a loop diagram is one where a photon creates an electron-positron pair, which then annihilates with itself. Here the intermediate electron can have any momentum, so we must integrate over all momenta, which leads to a divergent integral. This diagram describes the photon self-energy, or vacuum polarization. In his paper, Feynman highlights the importance of such diagrams. So far, we have only reformulated quantum electrodynamics without introducing new physics. Therefore, the problem of divergent integrals has not yet been solved. To solve this, some modification must be made to the theory, and Feynman recalls the modification that he proposed in his earlier paper, namely to substitute the delta function describing the electron interaction with a narrow function with finite width. As was demonstrated in the previous paper, this makes the divergent integral converge, and when physical quantities are calculated, they are found to be independent of the specific form of the convergence factor. This is the introduction of mass renormalization in the theory. The other diagram that describes vacuum polarization is also mentioned. A similar trick is applied to make the divergent integral convergent, and this is the introduction of charge renormalization in the theory. This concludes the discussion of Feynman's 5 papers. The final paper that we will discuss is the one by Dyson, where he demonstrates the equivalence of the Tomonaga-Schwinger theory and Feynman's theory. However, before we do this, it is worth pointing out some peculiarity in the publications on this topic. When we check the dates of publication, we find that after Dyson's paper, Feynman published 2 more papers. In fact, the 5th paper of Feynman that we just finished discussing was published after Dyson's paper. What did Feynman still have to add to this topic after Dyson had reconciled the 2 theories? Feynman explained that the publication dates don't mean anything. Simply because of practical reasons, some ideas were published a long time after their initial discovery. Feynman even admitted that his own paper was rather unnecessary, since Dyson had already proven the theory. But for his own purposes, he just wanted to show how he did it. So in his paper of 1950, he explained how he worked with the Lagrangian and path integrals, and how he then extended these methods to the Dirac equation and positron theory. In his paper from 1951, he explained how he performed calculations with non-commuting variables. When variables no longer commute, simple theorems no longer hold. For example, the exponent of a sum is no longer the product of exponentials. By introducing a new notation, one can again rewrite expressions in the familiar manner, which for Feynman simplified calculations in quantum mechanics. While these ideas were published more than 2 years after Dyson's paper, Dyson certainly knew of them beforehand. We will now discuss how Dyson proved the equivalence of the Tomonaga-Schwinger theory and Feynman's theory. While it was recognized that Feynman's methods were very effective, they lacked a rigorous mathematical framework. Feynman was quite comfortable using math that's not entirely correct just to express a physical idea. In the same way that a poet doesn't always strictly adhere to the proper rules of grammar, Feynman took liberties that might repel mathematicians. When he presented his work, he relied heavily upon physical arguments and intuition, but people were not always receptive to such reasoning, even if it led to correct answers. Therefore, it was important that Dyson demonstrated in a more mathematically proper manner that Feynman's theory was just as valid as that of Tomonaga and Schwinger. Dyson's analysis started with the Tomonaga-Schwinger equation, but for the sake of simplicity, we will consider the special choice of spacetime surfaces where the Tomonaga-Schwinger equation reduces to the Schrödinger equation. The time evolution operator is defined as the operator that transforms the wave function at some initial time to the wave function at some final time. By plugging this expression for the wave function in the Schrödinger equation, we find a differential equation for the time evolution operator. From this equation, we find a perturbative solution in a way that is similar to how we constructed the Born series. We start by integrating both sides of the differential equation. We use as a boundary condition that if the initial time and final time are the same, the time evolution operator should not change the wave function. The time evolution operator occurs on both sides of the equation, so we haven't yet solved for it. We can substitute the time evolution operator on the right side of the equation with the expression that we just found. When we expand the product, we find an expression for the time evolution operator that involves a zeroth order approximation, a first order approximation, and a second order approximation. We can continue to plug in the expression for the time evolution operator to find higher order approximations. This is called the Dyson series. The result is essentially the same as what we found when we solved the Tomonaga-Schwinger equation by dividing the spacetime volume between two surfaces into infinitely many slices. To connect this to Feynman's theory, Dyson noted that the basic principle in the Feynman theory is to preserve symmetry between past and future. For example, we saw that in Feynman's initial theory, the electromagnetic interaction was governed by both advanced waves and retarded waves, and in his more developed theory, electrons can travel both forward and backward in time. To see how Dyson incorporated this principle, let's consider as an example the second order term in the Dyson series. Here, the two time integrals have different upper bounds. To make the expression more symmetric, we make the upper bounds of the integrals equal, and we introduce a Heaviside step function to limit the integration interval. Since the integration variables are dummy variables, we can interchange them to find an equivalent expression. Then, to make the formula truly symmetric in time, we add these two expressions together and divide by 2. When we look at the effect of the two Heaviside step functions, we find that depending on which time is larger, the order in which the Hamiltonians are multiplied changes. We can therefore introduce the time ordering operator, which orders the operators such that the operator evaluated at the earliest time is applied first, which means it occurs at the right-hand side of the product. Therefore, we can rewrite the Dyson series by making the upper bounds of all integrals equal to each other and applying the time ordering operator to the integrand. By recognizing the Taylor series of the natural exponential function, we can write the Dyson series as a time-ordered exponential. The next step in Dyson's analysis is to change the wave function to a quantized Dirac field, so that the connection between the new Feynman theory and the more familiar quantum field theory can be demonstrated. We saw in a previous video that to quantize a field according to the field theory of Heisenberg, Pauli and Weisskopf, we decompose the field into eigenmodes and promote their coefficients to creation and annihilation operators. In the case of a complex-valued field, the creation and annihilation operators refer to different particles with opposite charge. For a Dirac field, these correspond to electrons and positrons. The creation and annihilation operators correspond to positive and negative frequencies respectively, which in turn correspond to negative and positive energy states. To describe the interaction of an electron or positron with an electromagnetic field, we multiply the forecurrent with the forepotential. The forecurrent can be expressed in terms of the quantum field via Noether's theorem. We want to calculate the matrix element corresponding to a particle scattering from a state A to a state B. States A and B can be described by a creation operator acting on the vacuum state. This creation operator becomes an annihilation operator when taking the emission conjugate of the state. The scattering matrix is the time evolution operator, where the initial and final times are in the infinite past and future. In the interaction picture, the time evolution operator is found by calculating time-ordered products of the interaction Hamiltonian. Each occurrence of the interaction Hamiltonian introduces a field operator and its Dirac adjoint. Each field operator introduces a sum over creation and annihilation operators. Therefore, the time-ordered product of multiple interaction Hamiltonians yields many cross terms of different combinations of creation and annihilation operators. Fortunately, we need to only consider those terms that yield a non-zero matrix element, which is found by taking a vacuum expectation value. Therefore, every creation operator for a certain state must be paired with an annihilation operator for the same state. The combination where an electron creation operator is multiplied with an electron annihilation operator is obtained when a psi bar is multiplied with psi. Because of the time ordering operator, this happens when psi is evaluated at a later time than psi bar. As we are integrating over all times, at some point the order of the two times swap. Then, because of the time ordering operator, the order of multiplication of psi and psi bar is swapped. Since we are considering a fermion field, swapping the two functions introduces a minus sign. With this order of multiplication, only the positron creation and annihilation operators give a non-zero contribution to the vacuum expectation value. Since each field operator sums over all modes, we find a sum of all positive energy states if the final time is later than the initial time, and a sum over all negative energy states if the final time is earlier than the initial time. This is the same as the expression for the Green's function that Feynman introduced, where electrons travel forward in time and positrons travel backward in time. Therefore, Dyson demonstrated the equivalence between the Tomonaga-Schwinger theory and Feynman's theory by introducing the time ordering operator and by showing that the vacuum expectation value of the time-ordered product of fields results in the Feynman propagator. Now that Dyson derived Feynman's theory more rigorously, using the familiar framework of quantum field theory, the theory could be developed further to make it more formal and systematic. For example, Wick's theorem gives precise guidelines on how to construct Feynman diagrams from the Dyson series, and the LSC reduction formula provides a formalism to calculate scattering matrix elements from them. One can also read the structure of Feynman diagrams directly from the interaction term of the Lagrangian or Hamiltonian density. For example, the interaction term for quantum electrodynamics tells us that at each vertex of the Feynman diagram, we have one ingoing arrow, one outgoing arrow, and one photon. We can verify that this is the case for the diagrams that we considered for Baba scattering and Compton scattering. For fields that have other interaction terms, the vertices have different lines. So Feynman developed a very effective method to calculate physical processes. But even though the methods are effective, the physical theory upon which they were built is not consistent. To remove the divergences due to self-interactions, Feynman modified the physical laws at short length scales, or equivalently, he modified the laws at high photon energies. It turned out that the physically observable quantities do not strongly depend on the precise form of the modification, so we can use this method to successfully calculate scattering matrix elements. But this means that the modified physical laws are arbitrary and almost certainly incorrect. In fact, the modified theory violates certain fundamental principles such as energy conservation. So while we can now successfully calculate observable quantities, we do not have a consistent theory of electrodynamics that we know is valid at short length scales. Feynman originally didn't want to publish his findings before he had solved this problem. But because people wanted to know about his calculation methods, he published anyway. When Feynman reflected back on this several decades later, he considered it fortunate that he published his findings before the problem was solved, because it still hasn't been solved to this day. We have made great progress in understanding the theory of renormalization. That is, we have been very successful in calculating observable quantities from a theory whose details we do not know at very short length scales, or high energy scales. But we have not been successful in formulating a sound theory at short length scales that is consistent with the observable electrodynamics at longer length scales. In other words, we obtained the theory of quantum electrodynamics by renormalizing something, but it has never been proven whether that something is a consistent theory itself.